Why does the flame of a gas stove have a blue color, while the flame of a candle has a yellow color? This is quite an obvious question, but giving a truly correct and, more importantly, complete answer turns out to be not so simple. We will need a rather extensive excursion into quantum mechanics, chemistry, whose laws are essentially consequences of the principles of quantum mechanics, as well as a number of other related fields. The journey will not be very easy, although I will try my best to spare my dear viewers from the bone-crushing mathematics that is almost inevitable when we talk about quantum mechanics. We will not only better understand why flame can have quite different colors in different situations, but we will also learn many new things about how the world around us is arranged. So make yourselves comfortable, dear friends, and let us begin. And let us start from the very beginning. Where does light actually come from? Or more precisely, electromagnetic radiation, of which visible light is a particular case in a certain range of frequencies and wavelengths. We already talked about this in one of our previous videos, and there I explained that electromagnetic radiation is caused by the accelerated motion of charged particles. And that is true, however. It is not the only and not even the main mechanism of the origin of electromagnetic radiation. In everyday life, we more often encounter electromagnetic radiation generated by the so-called radiative energy transitions of atoms and molecules. Electrons in atoms can occupy various energy levels, and by giving an atom a certain amount of energy, we can make them move from a lower energy level, where the electron is characterized by a smaller total kinetic and potential energy, to a higher energy level with greater energy of the electron. After spending some time at this very energy level, the electron then moves to a lower energy level, releasing the excess energy, for example, in the form of a quantum of electromagnetic radiation, that is, a photon, including, if the energies correspond, a photon of visible light. Where can an atom obtain this energy from? Usually, in our previous videos, we say that it receives it from another photon, which the atom absorbs in order for an electron to move to a higher energy level. In fact, there can be many sources, including the kinetic energy of atoms during their collisions, or, more precisely, during the so-called inelastic collisions, when a part of the internal energy is able to transfer into the internal energy of the colliding bodies. In the macroscopic world, this can look, for example, like heating, such as when a nail becomes hot after we hit it with a hammer. In the quantum world of atoms and subatomic particles, however, most often this energy goes into the transition of electrons within the atom to higher energy levels. Of course, atoms can obtain kinetic energy for such transitions not only from other atoms, but in general from any objects. For example, in gas discharge lamps, electrons accelerated by the electric field arising between the cathode and the anode of the lamp are used for this purpose. When an external voltage is applied, such a field can accelerate electrons strongly enough so that they have sufficient kinetic energy to excite the atoms of the gas. A similar process occurs in the northern lights. Only there, the source of energy is high-energy protons and electrons flying from the sun. The most important point here is this. Each atom has a specific map of energy levels, and accordingly, a limited set of possible transitions between them. For example, this could be a transition to the ground state from the first, second, or third excited level, a transition from the second or third levels to the first excited level, and so on. And each of these transitions generates a photon with its own energy and electromagnetic radiation with its own wavelength. This means that an atom of a given type can emit photons only of certain energies and light only of certain wavelengths. That is, the spectrum turns out to consist of specific wavelengths at which radiation occurs. It is said that the emission spectrum of atoms and of substances composed of these atoms, for example monoatomic gases, has a line-like character. By the way, in the comments under one of the previous videos, I was asked a question: how wide are these spectral lines of atomic spectra? In other words, how precisely are the emission lines of atoms defined? Perhaps right now is the best time and place to clarify this matter. For example, when an electron of a hydrogen atom makes a transition from the first excited level to the ground state, energy of 10.2 electron volts is released, which corresponds to a wavelength of 121.6 nanometers. This is ultraviolet radiation, the so-called Lyman alpha spectral line. However, if we try to measure this wavelength in an experiment, we will obtain slightly different results, a little larger or a little smaller. And the matter here is not the inaccuracy of our measuring instruments, but rather other, more fundamental things, the so-called broadening effects of spectral lines, which in practice will not be exactly lines, but rather bands, though, as we will now see, quite narrow ones. The first effect worth mentioning when we speak about atomic radiation is the so-called Lorentz broadening of spectral lines, which in turn follows from the uncertainty principle fundamental to quantum mechanics. One version of this principle states that there is a limit to the accuracy of simultaneously determining the energy of a system and the time during which this system will exist in a state with such energy. In this case, the energy is precisely the energy of the electron in the excited state, and the time is the average lifetime of the electron in this state. For the second energy level, 2p state in the hydrogen atom, this average time amounts to approximately 1.6 times 10 to the power of minus 9 seconds, which gives us an uncertainty in determining the energy of the 2p state of approximately 4 times 10 to the power of minus 7 electron volts. As can be seen, the Lorentz broadening smears the Lyman alpha line quite insignificantly. A somewhat more significant role is played by another effect, the so-called Doppler broadening, which, as its name suggests, is a consequence of the Doppler effect, according to which the wavelength, in fact, of any wave perceived by an observer, depends on the velocity of the source. We have all encountered this effect when a honking car passes by us. When it approaches us, the sound of its horn seems higher, and when it passes us and begins to move away, it suddenly becomes lower. With atoms and the light they emit, essentially the same thing happens. If, during chaotic thermal motion, at the moment of emission, an atom is moving toward the observer, then the observed wavelength will be slightly shorter, and if it is moving away from the observer, slightly longer. In the case of the same Lyman alpha line at room temperature of 300 kelvins, the amount of broadening will be approximately 2 times 10 to the power of minus 4 electron volts. And therefore the emission spectrum of atoms in reality turns out to be extremely close to line-like. The emission spectrum of gases composed of molecules is also line-like. Essentially, the processes there are almost the same, but with a number of important nuances. The map of energy levels of an atom is the list of allowed states of the electron in this atom during its interaction with the atomic nucleus, where each state and each energy level corresponds to a wave function that the electron possesses in that state. And from these wave functions, according to the rules that we talked about a little in one of our previous videos, one can extract information about the observable parameters of the electron at this energy level. For example, about its energies and momenta. However, this happens only in the case when we are dealing with a single, isolated atom. In a molecule composed of several atoms, each electron is bound not to one, but to several atomic nuclei, and of course its possible states, energy levels, wave functions, and energy values will be different. Fortunately, it turns out that the wave functions of electrons in a molecule are connected with the wave functions of electrons at the energy levels of the atoms forming the molecule by rather simple relations. Let us say, for example, we are speaking about electrons located at the very lowest energy level 1s for each of the atoms of the molecule. Let us denote the wave function of the electron for the first atom as psi1 and for the second atom as psi2. What will the wave functions look like for the very lowest energy level in a molecule composed of such atoms? It turns out that the wave functions of the energy levels of a molecule, its molecular orbitals, are all possible linear combinations of the wave functions of the energy levels of the atoms that compose it. We have, let me remind you, 2 atoms and 2 wave functions of their ground states, which means that there will also be 2 possible linear combinations, psi1 plus psi2 and psi1 minus psi2. To be precise, fully correct and rigorous notation would include a normalization factor in front of the bracket, which looks a certain way, but I promise not to dive into mathematics without real need. And for us, this is not so important. What matters more is that from 2 atoms, each of which has 1 electron state, we obtain a molecule with 2 states, different ways to combine the linear combination of individual wave functions. And of course, the energy of these states with different wave functions will be different. One can demonstrate, though I will not do it here, that the state corresponding to the sum of the wave functions will be characterized by lower energy, even lower than the energy of the original atomic energy level. But in the case of the minus sign, the energy will turn out to be higher, even higher than it was in the individual atoms. It is said that during the formation of a molecule, the splitting of energy levels occurs, and it is precisely this splitting that gives rise to the physical effects that form the basis of an entire science called chemistry. Indeed, let us consider two hydrogen atoms, each of which has one electron. When these atoms combine into a molecule, both electrons will occupy the lower energy level, and as a result, the energy of the system will be less than the total energy of the separate atoms. The process of molecule formation is energetically favorable and actually occurs. But for helium, the next element in the Mendeleev table, there are already 2 electrons, and for 2 atoms, their total becomes 4. According to the Pauli principle, only 2 electrons with oppositely directed spins can occupy one orbital. Therefore, all the electrons of a hypothetical helium molecule would not fit on the lower energy level. 2 of them would have to move to the higher molecular orbital with greater energy than the original atomic energy levels in the separate atoms. And it turns out that the energy of all 4 electrons in a helium molecule would be greater than the total energy of 4 electrons in separate atoms. Therefore, the formation of a helium molecule is energetically unfavorable and does not occur in nature. In chemistry, the orbital with the lower value of energy is therefore called a bonding orbital, while the one with the higher value is called an antibonding orbital. The more electrons are located on a bonding orbital, the stronger the molecule is, and the more electrons are on an antibonding orbital, the less stable the molecule will be. If my dear viewers are interested, then in our future videos, we can continue and develop the topic of the physical foundations of the existence of the laws of chemistry. But for now, let us return to the direct subject of our video. So, in a diatomic molecule, the energy levels of the atoms split, meaning that there are twice as many as in an individual atom. In fact, it becomes even more interesting. A molecule consisting of 2 atoms also acquires additional degrees of freedom, for example, rotational and vibrational, which contain additional energy. This energy will also be quantized, meaning that additional vibrational and rotational states appear, together with related energy transitions, including radiative ones. Thus, in reality, the formation of a molecule from 2 atoms complicates its spectrum not merely twofold, but much more. If a molecule consists of 3 atoms, then each of its energy levels splits into 3. For a 4-atom molecule, into 4, and so on. In addition, the number of rotational and vibrational energy levels for such complex molecules will also be greater. For the most complex molecules, we are speaking of thousands of energy states, between which the most diverse transitions are possible, and the emission spectrum of such a molecule becomes very, very complex. In our case, fortunately, the situation is much simpler. In the case of a hydrocarbon flame, such as the flame of methane in a gas stove, the main contribution to the glow comes specifically from diatomic molecules, or more precisely, radicals like OH and CH, which form at intermediate stages of the chemical combustion reaction. The energy released in the course of such reactions is spent, among other things, on exciting these radicals, and the transition back to the ground state is accompanied by radiation in the blue region of the spectrum, which is what colors the gas flame of the stove in those very shades. And everything would be perfect, if not for one but. In the flame of a candle, there are also the same radicals OH and CH, and in theory they also ought to color its flame blue. Yet this does not happen. More precisely, it does happen as well. If one looks more closely, then at the bottom, near the wick, there is also a region where the flame has a bluish tint. It becomes yellow in the areas where the temperature of the flame is higher. And now we move on to the explanation of why this happens. The formula of combustion of paraffin, from which a candle is made, looks like this. It is easy to see that for the oxidation of one molecule of paraffin, a very large amount of oxygen is required. In real conditions, there is simply not that much oxygen available to the flame, and therefore paraffin burns only partially, while partly undergoing the reaction of thermal decomposition. The resulting simplified formula, without stoichiometric coefficients, which depend on the amount of available oxygen, is written like this. In addition to carbon dioxide and water, carbon monoxide is also formed, as well as pure carbon, whose atoms bind together, forming solid soot particles. And in solids, the processes of radiation occur in a completely different way than in gases. We have already established that in the bound state of two atoms, that is, a diatomic molecule, there are more energy levels than in a single atom. In a triatomic molecule, there are more levels than in a diatomic one, and so on. But soot grains represent bound states not of 2, 3, or even 10 atoms. In the crystalline lattice of carbon, millions and tens of millions of atoms are bound together even in the very smallest grain. Accordingly, the number of energy levels here is no longer in the thousands, as in polyatomic molecules, but in the billions and trillions. In fact, there are so many of them that the comb of possible states merges into a continuous band. Strictly speaking, this band is not truly continuous. It still contains discrete levels, but the differences between them are so tiny that we cannot detect them even with the most sensitive instruments. We are speaking of quantities on the order of 10 to the power of minus 12 electron volts and less. Therefore, in solid-state physics, and more generally in condensed matter physics, which includes liquids, dense plasma, and so forth, people no longer speak about energy levels or states, but about, for example, the density of states in a given energy range, and so on. In fact, the situation is a little more complex and interesting. First, due to the Pauli exclusion principle, not all electrons of a solid can occupy the very lowest ground energy state. The states with minimal energy turn out to be filled, and transitions into them are in general impossible, so from higher energy levels, electrons jump down not all the way to the very bottom. Second, in most solids, with the exception perhaps only of metals, there is a white spot on the map of energy states, the so-called forbidden zone, a range of states that are not realized and that electrons cannot occupy. The forbidden zone is a very important thing, having key significance for solid-state physics. For example, its width plays a decisive role in the properties of semiconductors and other materials. We will definitely talk in more detail about what the forbidden zone is, where it comes from, and what it affects in our future videos. But in relation to our topic today, this fascinating question has no direct connection, so we will leave it for later. So since in a solid body practically any energy states are possible, the transitions between these various states produce an almost continuous emission spectrum containing nearly all possible wavelengths. Technically, this is again not a perfectly continuous emission band, but a set of very, very densely packed spectral lines, the spacing between which amounts to billionths and trillionths of an electron volt of photon energy. Whereas the natural broadening of spectral lines due to the same Doppler effect is 1,000 times greater than the interval between the lines, and therefore the observed spectrum truly appears continuous, from microwave radiation and radio waves to ultraviolet, X-rays, and even gamma radiation. This does not mean, of course, that solid bodies emit all wavelengths in equal amounts. For an active emission to occur, energy must first be transferred to the crystalline lattice, which must move into the corresponding excited state and then relax from it into a state with lower energy, which is what is accompanied by emission. The usual source of energy is the collisions of atoms during their thermal motion. That is, the energy that is spent on transferring electrons into a state with greater energy is, generally speaking, the thermal energy of the motion of atoms. And this energy is the larger, the higher the temperature of the body. At room temperature, for example, the average kinetic energy of thermal motion amounts to tenths of an electron volt, and the main energy transitions occur between levels separated by just such an energy difference. This means that in the emission spectrum of a body, photons with the same energy will dominate, which corresponds to wavelengths of tens of thousands of nanometers. This is deep infrared radiation, invisible to the naked eye. That is precisely why the emission of heated bodies at room temperature cannot be seen without a special device, a thermal imager. More precisely, in reality, the atoms and molecules of a body during their thermal motion can have a wide variety of kinetic energies, both significantly larger and significantly smaller than the average. The distribution of molecules and atoms by velocities is described by the so-called Gaussian distribution. It has a peak around that very average kinetic energy at the given temperature, which means that the fraction of molecules or atoms with those kinetic energies is maximal, and as we move away from the average value, the fraction of molecules with greater or smaller energies rapidly falls. Sometimes in a body at a given temperature, radiative transitions can occur with significantly greater or significantly smaller energy than the average kinetic energy of the molecules. Even bodies at room temperature emit some amount of electromagnetic radiation in the visible range. That is, they glow, only very, very weakly, so weakly that we cannot see it. If one carefully calculates everything, it turns out that for a body with a temperature of 300 kelvins, that is about 27 degrees Celsius, the visible region accounts for only a trillionth of the total emission. And each square meter of the surface of such a body will emit on the order of 10 to the power of minus 30 watts of light. This is about 1,000,000 billions of times less than what the human eye can detect. As a body heats up, the average kinetic energy begins to shift toward higher energies, which means that the fraction of high-energy, short-wavelength radiation in the spectrum also increases. At approximately 530 degrees Celsius, or 800 kelvins, the fraction of visible radiation becomes sufficient for it to start being detectable by the naked eye. Radiation in the red part of the spectrum becomes visible, then, as the temperature continues to rise, in the orange, yellow, and so on. It is also possible to obtain blue, violet, or even ultraviolet glow, but for this truly high temperatures of tens of thousands of degrees are required. Under earthly conditions, this can be achieved only in the arc of electric welding, while in space, such a spectrum is precisely what is emitted by the most massive and hottest stars. And neutron stars, whose surface temperature reaches millions of degrees, emit a significant fraction of their energy in the X-ray range, that is, in the form of ionizing radiation. The key conclusion is the following. A heated gas composed of individual molecules emits only at specific wavelengths corresponding to the chemical composition of that gas. But the radiation of solids, as well as liquids and other condensed media, depends almost not at all on the chemical composition of these bodies, and depends only on the temperature. And now we finally know enough to answer the key question of our video. Why do gas in a stove and paraffin in a candle produce different flame colors when burning? The flame of a gas stove or a gas burner, in which methane or another gas burns, is a pure flame whose glow is due to electronic energy transitions in molecules and free radicals. For natural gas, this is mainly the emission of CH and OH radicals. At the same time, it should be understood that only a very small fraction of the energy released during gas combustion is spent on radiation, since only a small fraction of molecules, even at a temperature of 1,000 degrees, possess kinetic energy corresponding to possible energy transitions between different states. That is precisely why a gas flame heats well but gives relatively little light. But in the flame of a candle, thermal radiation of soot particles heated to the same 1,000 degrees dominates. The very same type of radiation as that of any solid body heated to this temperature. Such solid particles convert heat into light more efficiently, since visible radiation can be produced by practically any transition whose energy corresponds to the wavelength of visible light. That is why a candle shines brightly, significantly brighter than a pure gas flame of similar parameters. During the burning of a candle, the same CH and OH radicals are also produced, and their molecular radiation also contributes to the emission. But this contribution is relatively small, and we do not notice the characteristic blue lines in the main part of the candle flame. We notice it only in the lower part near the wick of the candle. Where the flame temperature is significantly lower, the thermal radiation is weaker, and the pure spectral lines are still visible. So this is the rather non-trivial answer we had to give to the seemingly very simple question of why the flame of a gas stove and that of a candle have such different colors. However, there is a silver lining, because in the search for this answer, we were able to learn much more about how the world around us works. And we will certainly continue to learn more about it in our future videos. and I kindly ask everyone who enjoys what is happening on our channel to support its work by becoming a sponsor here on YouTube or on our pages on Patreon and Boosty. The link to the latter, as well as the corresponding QR code, should now be appearing on your screens. And that is all from me for today. All the best to you, dear friends, and see you soon again in our next videos.